Let's do an example now. If we have this kind of characteristic equation, 2s to the power of 4 s cubed plus 3s squared plus 5s plus 10 is equal to 0. Okay. First of all, we have to analyze the necessary condition. For the necessary condition, all coefficients should be the same sign. As you see here, this coefficient is positive, the second one positive, 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 and positive. Okay, this is satisfied. What about the second one? The second one is all of the coefficients should not be, any of the coefficients should not be 0. Let's check it. For the s to the power of 4, we have a coefficient. S to the power of 3, we have a coefficient which is 1. For s to the power of 2, we have a coefficient. For the s to the power of 1, we have 5. For the s to the power of 0, we have 10. So, this condition is also satisfied. So, what about the sufficient condition now? For the sufficient condition, we have to create Routh tabulation. Let's do this now. S to the power of 4, 3, 2, 1, and 0. The higher order coefficient is 2. After, we will get s to the power of 2, which is 3. And then we will use 10. What about the next row? The missing term, s to the power of 3, we have 1. For the s, we have 5. And we don't have, so it will be 0. Okay, let's find the other roots now, the other rows now. In here, 1 times 3, it will be 3, minus 5 times 2, it will be 10, divided by 1. So, we will get minus 7. What about this term? 1 times 10, 10, minus 2 times 0, you will get 0, divided by 1 again, it will be 10. We know from the rules, if any value is 0, the consecutive column values will be 0. Let's find this component now. Minus 7 times with 5, it will be minus 35. Minus 10 times 1, it will be 10, divided by minus 7. So we get 45 over 7. What about this term? This term will be minus 7 times 0, it will be 0, minus 1 times 0, it will be 0 again, divided by minus 7, so we have 0. What about s to the power of 0? We found a 0 here, so this will be 0 also. Okay, what about this term now? 45 over by 7 times with 10, minus 7 times 0, divided by 45 over 7, so it will be 10. That's all. After do that, we will analyze the first column of the Routh tabulation. We will analyze this column now. As you see here, we have a sign changing, positive, positive, and then negative. After that, we have also positive and positive. So this system will be unstable. If you find the roots of this system, you will get two roots as s is equal to 0.755 plus and minus j 1.444. For these roots, as you see, the real part of these roots is on the right half S-plane. Okay, so this system will be unstable. That's all. For this question, we have two sign changing, so it means we have two roots on the right half S-plane. Okay, so this system will be unstable. Let's continue now from another question or the special cases. We have some special cases for the Routh tabulation. What is the special case for the Routh tabulation? We have two special cases. One of them is the first element in any one row of Routh tabulation is 0, but the others are not. Okay, the first component or number in any row is 0, but the remaining part of this row is not 0. This is the first special case. The other of them, all row components are 0. Okay, if we meet the first condition, what will be happen? As you see here, if we find here 0, what will be happen? For the next row, we will use this as denominator, right? Denominator. So it will be infinity. Okay, this is the first special case. How can we solve this condition? Let's learn it now. For example, if we have this kind of characteristic equation, s to the power of 4 plus s to the power of 3 plus 2s to the power of 2 plus 2s plus 3 is equal to 0. Let me analyze to the necessary condition. As you see here, all coefficients are the same sign, and we don't have any vanish coefficient, so necessary conditions are satisfied for this question. Let me analyze with the Routh table now. S to the power of 4, 3, 2, S and S0. The first coefficient 1, 2 and 3. And the second row 1, 2 and 0. As you see here, S2 is calculated as 0. How? 1 times with 2 minus 2 times with 1 or by 1. It will be 0. If you find a 0, before we continue now, what about this number? 1 times with 3 minus 0 times with 1, 0 divided by 1. So it will be 3. In here we have already 0. 0 and 0. Okay, as you see here, this is the first special case for us. the first component is 0, but the other ones, any of them is different from 0. This is the first special case. So what will we do now? Please assign a very small value replaced by 0, such as epsilon. Okay, epsilon is so small value. Maybe you can accept as 10 to the power of minus 5, for example, 0.00001. Okay, it is so small value. And please continue to analyze. In here, what we find now, 2 epsilon minus 3 divided by epsilon. Okay, this component will be 0. It will be 0 and it will be 3 now. Okay, let's analyze the first column now. For the first column, is there any sign changing? It is positive, 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 of course. Positive, maybe we can write here positive small value. And what about this? 2 epsilon minus 3 over by epsilon should be greater than 0 for the stability. But it is satisfied or not? As you see here, epsilon is so small positive value. So the denominator of this equation will be minus. So we will get minus and plus again. So there are two sign changing. We can directly say system will be unstable. Sorry, not seeing sign. Also we can say if we have two sign changing, we may have two roots which have positive real parts. Okay, which have positive real parts. For this question, if you find the roots of this system, we get S will be equal to minus 0.091 plus and minus J 0.90 and 2. The other roots S1, 2, S3 and 4 will be 0.406 plus and minus J 1.293. As you see here, we have two roots which have positive real parts. It means it will be on right half S plane. So this system will be unstable. If we have such a kind of system, the other example now, for the other special case now, S to the power of 5 plus 4 S to the power of 4 plus 8 S to the power of 3 8 S square plus 7s plus 4 is equal to 0. This is the other question for us. What about this question? Let's check the necessary condition first of all. All coefficients are positive and no one is vanished. So we can say this condition is satisfied. We will analyze the sufficient condition now. S to the power of 5, S to the power of 4, s to power of 3, 2, 1, and 0. 1, 8, 7. What about s to power of 4? 4, 8, and 4. Okay, let me find s to power of 3. 4 times 8 minus 8. It will be 32 minus 8 divided by 4. It will be 6. What about this one? 4 times 7. It will be 28 minus 4 times 1. It will be 4 divided by 4. We will get 6. What about this one? How can we find it now? Assume that there are 2 zeros, okay, for to find this component. 4 times 0, it will be 0, minus 1 times 0, 0, divided by 4, it will be 0, okay? So the consecutive rows will be 0 for this clone, okay? Let me continue now. 6 times 8, 48, minus 6 times 4, it will be 24, over by 6, it will be 4. What about this now? 6 times 4, 24, minus 0 divided by 6, it will be 4. Okay, what about this row now? 4 times 6 minus 4 times 6, it will be 0. What about this? 4 times 0 minus 0 times 6, it will be 0 again. As you see here, all row components are 0. Yes, what will we do now? First of all, this is a special case for the Routh table. We will evaluate the last row to find this row. How? What is the last row? Before this row, we have this row as last row. How can we express this row for the function? It is 4 times s squared plus 4, and this is an auxiliary equation for us. How can we get it? For this row, as you see, we have s to power of 2. The first component will product with s to power of 4. What about the second component? It will be already s to power of 0. Okay, so 4 times s to power of 0. So we will get 4s squared plus 4. For the special case rows, we will use the derivative of auxiliary equation. The derivative of auxiliary equation with respect to the s, of course, we will get 8s. Okay, 8s. So we will use this equation into the special case rows. Now, here we have already 0. For the 8s, we can say it will be 8. For this component, we don't have, so it will be 0. If it is 0, the consecutive clone components will be 0. What about the last one now? 8 times 4 minus 0 times 4 divided by 8, it will be 4. That's all. We can analyze this condition as like that. Let me continue. to check the stability now. In here, as you see, we don't have any sign changing, so we can say this system is stable or not. What can we say? If you have this kind of special case, we can say for this question, for this kind of special cases, we can say this system is marginally stable or marginally unstable. How can we say? This condition is met if we have any roots on the imaginary axis. Okay? If we find this as roots, we will get some roots as s is equal to j and s is equal to minus j. What's mean for us? Two roots are on the imaginary axis. What is mean for us? This is marginally stable or marginally unstable. For such this kind of system, we will get at least one row. All terms will be zero. Okay. We can use this condition for another analyzing. For example, if we have another example now, if we have this kind of function s to the power of 3 plus 0.3 s squared plus 1,2,0,4,0,0,0 s plus 1.5 times with 10 to the power of 7k is equal to 0. In here we don't have the k values. Okay, we don't have k values, but we know k should be positive for the necessary condition. As you see, k should be positive to satisfy the necessary condition. The other necessary condition is no one is vanished, so it is satisfied also. Let we find the root tabulation now. S to the power of 3, 2, 1 and 0. 1, 1, 2, 0, 4, 0, 0, 0. What about the others? 3, 4, 0, 8.3 and 1.5 10 to the power of 7k. Let me find this point now. This term will be multiplied by this minus 1.5. Maybe we can write it directly from the lecture notes. 410.36 times with 10 to the power of 7 minus 1.5 10 to the power of 7k divided by 3408.3. Let me shift it. Yes. What about this term? This term will be 0 because we have to assume here 0. It will be 0. What about this term? This will be, if you calculate it, you can find 1.5 times 10 to the power of 7k. Okay. According to this calculation, let me check the k values now. As you see here, 1.5 times 10 to the power of 7k should be 0. It means k should be greater than 0. Sorry about that, greater than 0. Okay. What about the second one? 410.36 times with 10 to the power of 6 minus 1.5 10 to the power of 7k over by this term should be greater than 0 for the stability. If you analyze this inequality, you will find K should be less than 273.57 and also K should be greater than 0. So the total inequality condition for us 0, K, 273 and 57. K should be in this range for the stability. What if we evaluate K as 273.57? What will be happen? If we do this, in here, this term will be 0. So, what does it mean for us? As you see, all terms in this row are zeros. So, we have to use auxiliary equation for this row. And from this condition, we know also we have to some roots on the imaginary axis. If you solve this question, you'll find this equation s squared plus 4.1036 times 10 to power of 9. It will be 0. So you will get plus and minus 1097. J, of course. As you see, this condition is met when we have any roots on the imaginary axis. Okay, so you can also use for this specification as like that. Let me do another example. If we have s to the power of 3 plus 3k s squared plus k plus 2 s plus 4 is equal to 0. Okay, let's define the k value for the stability. S cube, s squared, s1 and s0. We'll start from 1, 2 plus k, 3k, 4. What about this now? 3k times with k plus 2 minus 4 over by 3k. What about this? This will be 0 because we will assume 0 for this clone, and it will be 0 also. You will find 4 for this component. Okay, let's evaluate the k value now. As you see, 3k should be 0, greater than 0. So k should be greater than 0. What about the others? 3k times with k plus 2 minus 4 divided by 3k should be greater than 0. If you solve this inequality, you will find k should be greater than 0, k should be less than minus 2.528 and k should be greater than 0.528. So if we evaluate this condition, we can easily disregard this inequality because we know this k is greater than 0 already. If we evaluate these two conditions, we can decide to k should be 0.5, 2, and 8. This is the condition for the stability. That's all.